So I'm just going to introduce this webinar. We're going to have presenters Dr. Mirjam Wiedemann from UNSW Aviation and Dr. Georgios Konstantinou from UNSW Engineering, specifically the School of Electrical Engineering and Telecommunications. And we're going to explore whether electric flights are ready for takeoff. And if we look to the future, what are the challenges specifically with the grid and other energy-related questions that we need to tackle or consider? This is going to be covered in today's webinar. So we're going to kick off with roughly 30 to 35 minutes of Dr. Mirjam speaking, and then Associate Professor Georgios will speak for another 10 minutes, and then we'll have Q&A for 10 to 15 minutes at the end. Great. Thank you for joining, and over to you, Mirjam.
Okay, thanks a lot, Sharon. So welcome, everyone. Really delighted that some of you could join us here in person today. We have many more registrations, and I assume people looking forward to the recording. So we embarked on a journey in the last few months to look at infrastructure, or in particular grid needs at airports to help the transition to sustainable aviation. And you will see throughout the project that that is not only electric flights, but that we also looked at a whole lot of other drivers, and including hydrogen flights. But before I start, I need to acknowledge and really thank a whole bunch of companies and individuals who really provided insights and real-world data to us. And in particular, I would like to thank the Digital Grid Future Institute for funding for this project, and of course, our two research assistants, Annelien Wee and Shenglong Gao, who are also in this call and will supporting the Q&A as well. So we will start with introducing the airport precinct and how we defined it and what we looked at, what are the drivers in the precinct, and what's about sustainable aviation and where we try to go from here as an industry. Then introducing the 10 different scenarios we looked at for 2030 and 2035, and 5 scenarios for 2050. So these are 5 distinct scenarios with the difference between base and high passenger numbers. You will see that a little bit later. Then we'll give a brief introduction to the 2 case studies. That's Newcastle Airport and Shellharbour Airport, who were kindly enough being our case studies for this project. And then I will hand over to Georgios, who will explain the modeling and actually the findings for the grids before we finish with some main findings and Q&A. So decarbonization of aviation, there's a lot of talk about that in recent years, but we hear a lot about SAFs, we hear about electric flying, hydrogen flying, but we are not hearing so much talk about the infrastructure that is actually paramount to enable that transition. And of course, the airports are at the forefront of that transition to enable and support these electric and hydrogen flights and new technologies such as drones coming into that environment. So we have as an industry a goal to reach net zero by 2050. And we have a whole bunch of measures or factors where we are trying to achieve that. We are looking at airport carbon accreditation. We are looking at alternative fuels like SAFs, sustainable aviation fuels, electric flying and flying with hydrogen. We are looking at new technology, at new aircrafts powered by these new fuels. We are looking at drones. We are looking at more fuel efficient aircraft. That's nothing new. We have done that for decades. We're looking at more sustainable material to build the aircrafts, and we are looking also at flight route planning to conquer contrails. For this project, only important are the alternative fuels and the new technology, and to a certain amount the airport carbon accreditation, because for level 3, for example, that looks at the third-party emissions, and that's obviously at the airport. The flights, or a big part are the flights, so massive interest there for the airports as well to decarbonize these flights and supporting alternative fuels and new technology to decarbonize flying at that airport. We needed to define the load growth drivers and try to find out what is actually impacting our electricity grid at the airport. And one thing was also first to define what is actually the airport precinct. So we defined it, it's airside and landside for the aviators who are here today. For everyone else, that is basically the boundary of the airport, where the airport has control over the land. And we also looked at substations and meters that are actually allocated to the airport operator. When we started looking at the airport precinct grid, it got much more complicated, I think, than we originally assumed. And as more as we thought about it, and as more as we looked at it, as more factors were showing up. So we have increasing passenger numbers, and I will go through all of these factors a bit more in detail in a second. We have increasing flights due to increasing passenger numbers and a wider variety of fuel sources coming in or are already happening. We are seeing ground transportation for passengers and staff, cars and buses at airports globally, also trains, not so much at Australian airports. That impacts the grids because we are looking at electric vehicles. We're having ground transportation on airside in terms of ground support equipment at the airport that is increasingly electrified. We are seeing ground transportation on the cargo side if we have bigger cargo facilities at the airport, with trucks being electrified as well or run on hydrogen. We are seeing huge landside developments called Airport City. These are business parks on the land side, a lot of real estate. And these office parks and warehouses, of course, need electricity as well. But we also have airports who are already generating electricity, mainly through solar panels. So for everyone who's not from aviation, you may remember COVID and our passenger numbers nearly disappeared completely. But we have a lot of different forecasts. We are back to growing passenger numbers. We are now pretty much globally back on the 2019 levels before COVID hit. And all projections clearly show an increase of passenger numbers in the next few decades up to 2050. Looking at different fuel sources, of course, we have the sustainable aviation fuels. You hear much more about that nowadays in the news. That is not important for this project because we assume they're trucked in the same like jet fuel stored maybe at the airport, so similar, but it's not impacting our grid. Hydrogen could be trucked in as well, the same like jet fuel, and probably will be in the beginning. However, once it's scaling up and we need a lot of hydrogen at airports, we do assume that we will see production on site, what will require new infrastructure and electricity as well. For the electric flights, of course, they need to recharge at the airport, and that will have quite significant impact on the electricity grid, as we will see in the results a little bit later. We are also not only looking at conventional aircrafts, but also increasing use of drones, including large-scale drones for passenger transport, and those are powered by electricity and hydrogen. So where are we now with all of that? I always have the feeling everyone talks about nothing else, but that's probably because that's my network that talks a lot about electric and hydrogen flights. For electric flights, we have, for example, the Pipistrel Velis Electro, a general aviation flight, or an aircraft that's also used for training purposes. Certified flying, sold its 100th unit in March this year. So definitely not only on its way, already flying. So we will assume an increased uptake of general aviation aircraft that are powered by electricity in the coming years. Hydrogen flights are on the way and being tested and flying and on the way to be certified. Will take probably a little bit longer, especially for commercial short-haul and medium-haul flights. We have for electric flights and hydrogen flights companies globally who are working on it. 2 Australian companies I want to acknowledge in those areas is Dovetail and Stralis. Both provided us nicely with their data for this project. And when we look at drones and AAM, we see the first ones are certified. We see the first ones globally flying. We do assume that we will see them in the next few years in Australia as well. A lot of the international examples don't have a long range. We have an Australian one from AMS Aero that is looking at a range of 1,000 kilometers. So that will be a game changer for the Australian landscape, but it will take a few more years for certification and flying. But all of that is expected to happen before 2030. For ground transportation, passengers and staff who are coming into the airport precinct, we see, of course, an increasing use of electric vehicles globally, but also in Australia, it's now taking off quite a bit. That's a picture on the right. And also, when we look at buses, all states and territories have plans for electric bus fleets. For this project, we looked at numbers for New South Wales as both our case studies were in New South Wales. And of course, globally, trains could impact the grid potentially as well, but it's not so much of a factor for Australia. Ground support equipment, increasingly electrified internationally. We have seen that, I think, for at least a decade. In Australia, we also have airports that are having completely electrified ground support equipment, and it's moving now very fast. So we do assume that it is underway, as it is for both case studies, and it will, the whole fleet will be electrified in the next few years. For cargo, especially if we have an airport precinct that has a big cargo facility, we would assume that trucks on hydrogen or electricity coming into the precinct, they would usually not recharge necessarily in the airport precinct, but we do acknowledge that once they're scaling up, that we may need, and you will see that in the scenarios, 1 or 2 trucks may need to charge occasionally at the airport, and it will impact the grid. There are a few challenges around electric trucks in Australia at the moment, based on Australian design rules to use international models. But I think from all what I have seen, this is way on a way to solve that. And we also see Australian companies looking at manufacturing or remodeling trucks to become electric or hydrogen powered. Landside development, call it airport cities, business parks. We see much more development around airports on land sites in terms of commercial real estate. We also see much more retail happening inside of the terminals. So those developments will also impact the need of electricity in the airport precinct. Electricity generation, interestingly enough, we do see airports that having some wind parks, but we're seeing much more profound use of solar panels on empty land around or vacant land at the airport, on roof of terminals, on roof of hangars, etc. So that's already happening and is assumed to increase over the next few years. So with all of that information, we needed to make scenarios for our modeling. So we looked at 2030, 2035, and 2050. And as said before, even these are 10 different scenarios. 5 are distinct ones. The difference between the 5 and the 10 are that the passenger numbers are changing. So for 2030, our scenarios, we call them kind of business as usual, because we do assume that we see the first AAM flights, we see a bit of electric and hydrogen general aviation happening and in the drone area as well, but not on a high scale yet, mainly because we have airlines that are not ready to retire their current aircraft, that it needs quite a bit of investment to buy new aircraft. It's also difficult for general aviation providers as well to renew their aircraft to a more sustainable aircraft. For 2035, we say electric and hydrogen flights have truly arrived, and electric and hydrogen will be used for all flights. And we also assume that for electric vehicles, someone has come up with a smart charging system, management system, so that not just when people plug in their cars, they get charged, but that management system would organize charging in a way to manage the load and the demand on electricity. You will see that is profound in the airport precinct, because when you assume that at the very busy time, when all flights are coming in, all staff is there, passengers arriving, rental cars are coming back, if we do not find a way to manage that load, they will all plug in at the same time, and there will be a huge amount of electricity at the same time. We need the electricity for the electric flights. For 2050, that's where it's getting really interesting. And of course, there is a whole lot of uncertainty around what's happening between now and 2050. So we looked at 3 different scenarios for 2050. And the first one was, we are saying, okay, hydrogen, electric, and SAFs will all be there, all parallel to each other in a different percentage. And we assume that the hydrogen is trucked in. For scenarios 7 and 8, we said all hydrogen, electric flying has disappeared, and seeing what that means for the grid if we are producing all hydrogen we need in the airport precinct. Scenario 9 and 10, then the opposite, all electric, hydrogen has disappeared in aviation, and of course that's huge impact on the grid, as Georgios will show you in a few minutes. I will talk a little bit more in detail to the first scenario and then a bit faster to the others, because it's repetitive and there are only certain areas that are changing. So these are our input factors for the scenarios. We had the passengers, and we had a bias and a high prediction of passenger numbers for one of the cases. That's where the scenarios are doubling. That's the only change between scenario 1 and 2. And the first passenger impact is the impact of increasing passenger numbers on the load, electricity needed for terminal and retail. So assuming that we have more passengers coming to the terminal, that means that at one point we need a bigger terminal, but it also means we are getting, for example, to start with, more restaurants, more coffee shops that are all require electricity as well. For flights, we said 2030 general aviation, we will see some uptake of electric flights in the area of general aviation, and the other 50 will be conventional or SAF, also no change for our grid. Cargo drones, we see assuming 50% flying electric and 50% of hydrogen. For IAM, so passenger or big cargo drones, we assume there are only a couple operational for maybe scenic flights or medical reasons, and they will run on hydrogen. For the commercial flights, we assume for 2030 no change yet, and that they will run on current regime or SAF. As I said earlier, as we assume 2030 is kind of close now, when you think about that the airlines would need to retire the current aircraft, getting new aircraft into service, etc., etc. We assume it will take a little bit longer, at least in Australia. For the ground equipment, already widely used, and we assume that it's charged outside of peak hours, and it will be used during peak hours, so it was important for consideration of the load. And they cannot be used as battery or vehicle to grid, as they will be operational during peak times. Electric vehicles, that was an interesting exercise. So we looked at the numbers for New South Wales. So for example, for 2030, there is an assumption or modeling that we will see 8% of the fleet in New South Wales to be electric. And that has become a number for our modeling in terms of chargers that need to be available. We assume by 2030, we don't have any dedicated bus or truck charger available. We do not assume that we have any kind of smart system that will organize how our electric vehicles being charged. So we assume when people plugging in, that charging starts. So we assume 50% of the chargers would be utilized at same time and at peak load at airport. And it's peak load because, or at peak time, because passengers and staff are arriving and being there. They plug in when they arrive. Rental cars are returned, they are plugged in. The only difference is the airport-owned vehicles would typically charge before and after peak times, as they would be used during peak traffic times. And the rest of the load, we assume, is distributed over the rest of the day. For landside development, we looked at where both case studies reasonable or early in their development. On landside, we said total available land, we are assuming 65% built up in total, so the rest will be empty space or green space. And by 2030, we will see 20% of that development has happened. We are looking at an average of 4 stories and a continuous load from 9 a.m. to 5 p.m. to power these offices, warehouses, whatever is being developed there. Other inputs, flight numbers, electric vehicles, and ground equipment increase by passenger numbers as a multiplier as well. As we assume electric vehicles, it's not only the percentage of the fleet of the state, but also that means a higher percentage of people coming to the airport precinct as our passenger numbers increasing, our flight numbers increasing, of course, the same as passenger numbers increase. Also, there were some challenges around. We don't know how big these aircrafts are. We do not know the routes. We'll talk about that a bit more in a minute. And the ground equipment needs to increase as well according to an increase of flights. So for scenarios 3 and 4, what is changing is that in 2035, we assume general aviation has become 100% electric. We see cargo drones 50% electric, 50% hydrogen. We see the first big passenger drones as transport run on hydrogen. And for commercial flights, we assume that 25% have been arrived running on hydrogen, while 75% are still running on the current regime or SAF. The one other change, or 2 small changes, are we have one dedicated truck charger that needs to be utilized where a truck needs to charge in 1 hour time due to cargo facilities. And someone has been developing a smart system and management system to organize the charging of the electric vehicles by distributing a bit more the demand on the grid, so that we only have 25% of chargers would be utilized at the same time and at peak load. For the landside development, that has increased to 50% build up. In 2050, for our first scenario, that's a mix of electric, hydrogen, and SAF, we assume general aviation is 50% electric, 50% hydrogen. Cargo drones, 50% electric, 50% hydrogen. AAM, we see regular passenger transport run on hydrogen. And for the commercial flights, we see 25% run on the current regime of SAF, 40% on hydrogen, and 35% on electric. We assume that the hydrogen is trucked in and that electric batteries have achieved medium range for our medium haul flights. We also see 2 dedicated truck chargers, as we assume their cargo areas have developed. One dedicated bus charger in case we have much more public transport and a bus would need to recharge in the airport precinct. So they would be charged on high rate at peak load. And the electric vehicles, we only have 15% of chargers would be utilized at the same time and at peak load, because we assume by 2050 chargers are widely available. People charge more at home. Batteries have gone so good that they don't need to charge so often, etc., etc. So it takes a load for the electric vehicles. It's getting lower. Landside development, we assume that we have 100% fully developed business parks at these airports. For all hydrogen, of course, what's changing here, we see all flights running on hydrogen and the hydrogen is produced on site. All electric, the opposite, everything is electric flying and hydrogen has disappeared as an option in aviation. So briefly, the 2 cases we looked at, Newcastle Airport and Shellharbour Airport, north and south of Sydney, 2 regional airports. For Newcastle, we have assuming that they're progressively developing into a small international airport with a wider catchment area, that they see bigger flights coming into Newcastle, We looked at the hunter's economic ambitions, and therefore we assume that the cargo facility that is being discussed will be operational in 2035 and has expanded in size by 2050. That's where the truck chargers are coming in. And the landside development would grow into a full airport city, full business park with more individual and public transport to the precinct. And the electrification of ground equipment is already on the way. And therefore, by 2030, it's well and truly done. Shellharbour Airport, a bit different case, very small airport in the south at the moment. We assume it grows into a small regional gateway airport. Council has adopted recently to increase or introduce security at the airport, and that would mean the airport would see much more and much bigger flights coming in. They are already having quite a bit of general aviation traffic, and we do assume it would increase for tourist, recreation, and medical reasons as well. And the airport becomes a significant site for cargo drones and AAM traffic. And the business park that's being developed will be fully developing as well. For ground equipment, we assume electrification will be fully achieved by 2035. So a few numbers behind us, current passenger numbers for Newcastle and Shellharbour, as you can see. And the assumption or the main differences for these airports are that for Newcastle, we do not assume any major general aviation traffic due to their location next to defense and being restricted in terms of flight numbers. For Shellharbour, we would assume very high traffic numbers for general aviation and expect them to increase. Cargo drones, no major use for Newcastle, but potential for a major drone base in Shellharbour. AAM, similar, very limited traffic anticipated for Newcastle due to the location, but very major traffic for Shellharbour, and the commercial flights would grow accordingly to the passenger numbers. So, and then we try to get that all in our model with all the assumption. And the last slide, I will talk about some of the assumptions and challenges we were facing. The biggest challenge was really how to model the flights, as we do not know neither what the aircraft will look like, for how big they will be. We do not know how much electricity they need or hydrogen in the future. We do not know the flight pattern. We do not know the routes. So what we did, we looked at the current routes and the current flight pattern of both airports. We looked at the kilometers they are flying, and they looked at the passenger numbers, and we modeled it as pax kilometer and increased that by the passenger numbers of the future, the predictions. And when looking at current batteries and energy needed of aircraft that are already existing, we realized it's 0.22 kilowatt hours per pax kilometer. That's what we use to model for the electricity. And for hydrogen, it's 0.006 kilo per pax kilometer. And then producing the hydrogen, we would need 55 kilowatt hours per kilo. Passenger numbers, these were predictions, real predictions that were coming from the airport, impacts the base load in terms of terminal and retail, and becomes a multiplier also for the peak load for all of electric vehicles and flight numbers and ground equipment. Electric vehicles, we followed the prediction for New South Wales and also included the passenger number growth as a multiplier and used current EV chargers. Ground equipment is growing depending on passenger numbers, is being charged outside of peak. Trucks and buses, as I have explained, for the different scenarios. And the landside development airside, we assume 65% build up, 4 stories average, a constant load between 9 a.m. and 5 p.m. and 0.014 kilowatt hours used per hour per square meter. Okay, so with that, I'm handing over to Georgios to show you these really exciting results. Thank you.
All right. Yes, thanks, Mirjam. From our side, you have seen so far that there were a lot of assumptions across a very diverse number of cases that we had to consider. So we chose to do all these assumptions considering the numbers and the energy requirements separately. So we wouldn't want to make any assumption about the energy that we're going to get in the airport precincts before we model these future developments. And once we had all of these numbers that Mirjam has been explaining for the last 20 minutes, we tried to put them in a model and then try to see what is the general consumption we would need throughout the day. So we're looking at general kilowatt hours that we would expect to be required at the airport for the whole day, and then also try to see some patterns in terms of the consumption at the terminal and the car park, the daily profile that would have at the whole airport precinct, excluding the flights, because the flights were a whole different beast by themselves, and then also introduce the flight part in our models, and then see what we would be expecting to see in these 5 or 10 scenarios that would analyze for 2030, 35, and 2050 for the 2 airports that we're using here as cases. The figures themselves in the next slides are going to be, in terms of format, very repetitive because we try to keep this consistent format so you can see the changes. At the top left here, we have what is the terminal consumption we are projecting from 2030, 2035, and 2050. We are basing this on the actual consumption and the daily pattern that was provided to us. So the numbers and the multipliers for all the assumptions directly affect this consumption. The car park, again, with all the charging number of electric vehicles we'd expect, trying to also put a pattern into the charging of the stations and the charging of the cars, the arrivals, departures, also the staff that is working that might require to charge their cars on the precinct car park. We also make our assumptions for the ground vehicles and when they will be charging, and you'll see how we distribute them throughout the day or mostly throughout the night when the airport is not operating. That combination of the top 3 plots that you see creates the right middle figure of the daily profile for each individual airport for each of the scenarios we're considering. Then on top of that, we will add the flights. And once we put all these numbers together, we're trying to see impact on the power requirements and also in the energy requirements for our future projections, starting from the numbers we had available to us today. So the first case we would consider here is the 2030 case where we assume that we still have sustainable aviation fuel and jet fuel available at Shellharbour. So only one case here for the passengers. So we will have this terminal pattern consistently appearing throughout the next 5 slides. And with all the assumptions coming together, the patterns that you can see are here in front of you. We also try to annualize that so we could see what happens throughout the year. So we kind of set some expectations on what would be the investment or what would be the requirements for power and again for energy that we would need at the airport precinct. The other thing we made as an assumption, because our plan moving forward for this project is to start looking into optimization and development for the future renewable generation in the airports, is to assume that the systems that are already present, the solar systems are already in the 2 airports, do not change in size. We would want to optimize for the available amount of solar that we want to install based on a particular project moving forward. So straight to the numbers. To go quickly through the remaining slides, we do see that at 2030, with the increase of electric flights in general aviation here at Shellharbour, the total consumption will grow to something in the area of 2 million kilowatt hours per year. And that is mostly driven by the changes in the electric flights in terms of charging. We also try to align that with the PV production, but the solar system that already exists there is quite small. So the impact we do see having in the local grid is quite small. You can see that in the number in PV production and also in the total grid energy purchase that we have. Then in our second case, looking into 2035, we see the numbers changing. We see the flights now becoming, we have a different pattern in the electric flights that we expect to see, which changes the pattern of flights and the electrical requirements that they impose in the system there. The daily profile changes quite a lot because we do now have ground vehicles and we have car parks that we need to provide more power. So the 2 waveforms change here. And we also, as we expected, since we have all this growth, our consumption increased by around 30 to 35% from the previous number. Again, the solar system does have a very small impact on the overall consumption. It is multiple orders of magnitude lower than what we expect to require in order to power flights and all the extra electrification of transportation we see at the airport. Then going into 2050, where the numbers start becoming really interesting and should show some hints of future conversation of how we handle electrification of airports. We do see that if we assume that hydrogen and electric is a mix, and we also need to supply directly all the flights with the flight patterns that we have assumed, then we do expect to see, if we do not do anything to manage, substantial peaks throughout the day. So I have circled them here in these results. They become quite high because the pattern of flights and the charging infrastructure we need will require quite a lot of power. So comparing to the numbers that we have for 2023, with our projections for 2050, we see an increase of 403 times in the power that we need to supply at a given time, the peak power that is required during the day. Now, the energy would be a bit different because you realize that there isn't much happening throughout the night. And with the hydrogen assumed here to be tracked in, we'll look at the total increase in the energy required at the airport by around 147 times. So the peak part of the power being an important component here. But again, this is an assumption of direct charging. Quite confident that there would be some solutions of energy storage and also managing high speed charging, high power charging of electric aeroplanes, and different input from the grid, so you can balance the power you need instantaneously to charge a plane and what you absorb from the grid at any time. For our next assumption, hydrogen only, and here we assume we are locally producing the hydrogen, so there is an assumption that there is a local electrolyzer that does all the hydrogen generation. The positive thing here is that we can keep this operating 24 hours a day, so it gives us a very smooth pattern in the consumption. That's why flights are just give a constant value. That hydrogen then can be stored and supplied to the aeroplanes. The two together lead to a substantial increase in power because everything is powered by hydrogen. So 376 times more in the peak power and around 600 times more in the energy that you need to supply at the airport throughout a year in order to support hydrogen-only flights by 2050. These numbers again become even larger when we consider electric only, simply because we do not have the storage included in our analysis, and this doesn't smooth the profile that we have in terms of power. So you can see here a substantial increase in the flights, 1,000 times more power and around 385 times more energy required on site to power the flights. Now, what we have not shown here is the impact of the landside development, because with the assumptions and the numbers and the growth that is projected, that becomes a quite high number that would distort substantially. And because we assume a constant pattern throughout the day, we eventually would need to include that, but we haven't done in this case. We have done the calculations for how much energy you would require per day here, but we have excluded that from our later analysis in terms of what we need to supply to the airport itself to support electric flights. Now, Newcastle, the case that come later, we have made two different assumptions for the passenger numbers, so a base case and a high case. But in terms of what we see for numbers, obviously different scale because different passenger numbers and different flights, but the conclusions will remain very, very consistent and very similar. We see an increase in the very first year, the 2030 year, because of the extra electrification of the electric vehicle fleet and also the ground station. With our flights having a secondary impact on the grid, simply because we do not assume a lot of general aviation on this particular side. And this stays consistent between the base case in this slide and the high case that we have in the next scenario. So the energy consumption as a total increases slightly, simply because we have more passenger numbers coming through the terminal. Now, in 2035, when we maintain we include hydrogen, we have this assumption of part of the planes being charged locally, but our hydrogen is coming from outside, so we do not have to install extra generation for hydrogen. And again, we do see this doubling from 2030 and 2035 of the total energy we require, and this kind of gives us an indication of what will happen. Now, once we get to 2050, we have 6 cases here, and the numbers, as we explained before, become very, very high very quickly. In a base case where we split everything by a third, we see an increase in the total energy we require by around 60 times, and the peak power increasing up to 300 times. Again, assuming that we do not manage it throughout the day, which probably we will need to do it, as you can see from these waveforms. That is consistent again for the base case and the high case that we have here. Things become even more extreme in the hydrogen-only case, constant power generation throughout the day, a peak power of 435 times and the peak energy of 234 times throughout the whole year. In the base case, and roughly the same numbers, just a small increase because of the multipliers of the extra passengers in the high case. Now, if electric aviation becomes the solution in 2050 and we need to charge our electric planes from the grid that is supplied to this airport, the numbers are going to become quite extreme here. The total power we would require would increase on an instantaneous basis by around 700 times in order to supply all the routes that are planned for the airport, and 147 times or 150 times here for the total energy. And once we go to the high case for the passengers, we see this 170 times more energy. That is smaller than we would require for hydrogen because we do have the extra conversion losses, but the peak power would become almost 1,000 times higher than what we have today on site at Newcastle. So if we try to, again, the landside development, similar pattern, similar numbers, they need to be included, whether that is supplied by the same route from the same substations that you have for the airport or not would become a question. From the numbers we see here, we probably think that this would be a separate supply to consider for the landside development. So two separate projects where you can have two separate systems. Now, to summarize our main findings based on the modeling that we have here, which gives us effectively the basis for moving forward to try to do optimization and trying to understand what sort of systems in terms of storage, in terms of local generation would require. We see that the terminal as a load in the near term and especially in the future becomes secondary. The main challenge revolves around how do we manage the electric vehicle fleet? What do we do in terms of peak hours? Especially because we have all the electric vehicles arriving at the same times and then departing at similar times. In 2035, we do see the first requirement for managing the network a lot strongly. So we need something that will allow us to save the peaks that we observe that are becoming higher and higher, maybe shift the time that we consume the load. That kind of hints towards the requirement for energy storage. Again, direct charging of electric planes, we see that from 2035, the numbers we have here will introduce a massive load into the network and have massive strain into the airport supply. We do think that we do need some sort of local storage to manage this particular case. Now, moving to 2050, the mixed scenario is the one that does require the least additional infrastructure because we assume a lot of things are coming from outside the airport. But we do need the whole development of a hydrogen supply chain that will be able to supply this extra hydrogen to the airport for 1/3 of the loads, and electric flight, again, adding some load that we need to manage. For an all-electric flight scenario, we see that we need a peak of up to 1,000 times if we do not manage it properly. And that is a substantial increase compared to what we have right now in the regional airports. For an all-hydrogen flight, the 24-hour generation does help us manage a bit the peak powers, but in terms of energy, we do require a lot more. The landside developments would be a major driver for the electricity needs. And again, we might start thinking about developing them separately in terms of supplies. But again, build-up of local generation, integration of energy storage systems, an integrated solution that would consider a local microgrid, smart charging, changing the power that you supply to the airplanes versus what you absorb from the grid, and a more coordinated solution is certainly the way forward as if you plan to expand your infrastructure to support electric flights. And with that one, Mirjam, do you want to put some final words before some questions?
No, thank you very much. I think what's very clear is that we do need to look at the infrastructure at airports if you're serious about sustainable aviation, and considering all the potential solutions and probably also thinking about where the funding is coming from to get the airports ready for sustainable aviation. Thank you. Over to you, Sharon. I don't know if you have any questions.
Amazing. We don't actually have any questions, but we can open up and perhaps just see if anyone wants to put their hand up. Oh, Emma.
Yeah, hi. I just wanted to ask a quick question. Did you distinguish with hydrogen between liquid and gas? Did you do any sub-analysis around that?
No, very good question, Emma. No, we didn't dig into detail of hydrogen production or difference between what kind of hydrogen is being used in aviation.
Okay, because with liquid hydrogen, which I think is going to be the main form of hydrogen that is likely to be used in flights, there'll be another stage of processing, which is liquefaction, which will also obviously use more energy. So that's just perhaps a consideration for any next stage research. And a lot of the hydrogen will ultimately be used in hydrogen electric aircraft. So the aircraft is still essentially electric. It's just hydrogen's being used to generate the power.
Yeah, good point.
Yes, to add on to that, the change that would have for if we start considering all these extra details will change the amount of energy we would require as to generate that kilo of hydrogen for the assumption we make for the passenger kilometer consumption. So that we could see that scaling up the numbers. So if we find these numbers, we should be it should be relatively straightforward to implement in the numbers that we've already shown here. That's a very good point. Thank you.
Civilian aviation, do you have any thoughts or insights on the challenges or opportunities of decarbonising military aviation and infrastructure, or is that impossible to model?
Well, we didn't look at defense at all. I think defense is always a very different beast, and but I do know they're looking, well, from what I know, electric and hydrogen is something they look at as well, but I have no insights per se in that.
That might be something that the Defence Trailblazer is addressing, but it's a good point. Thanks for that. We've got Paul Ferguson who's got his hand up.
Yeah, I just wanted to say thank you to Mirjam and the team for all the work that they've put in and sharing this information. It's been very insightful, and yeah, well done, team. Thank you very much. Puts us in a good step understanding what our potential consumption will be and ways to move forward, and wraps in quite nicely with our new master plan that we've just put together. So thank you, team.
Excellent. Thanks you, Paul, and thanks for your time and your insights and hosting me, visiting you in your office.
For the benefit of the rest of the group, where is Paul from?
Shellharbour Airport.
Shellharbour Airport, right, got you. Okay, great. Thank you.
If you have any follow-up questions or want to get in contact with us to discuss it further or discuss it for your airport, for any of the aviators who are in this call, feel free to send us an email.
I will also add here that there's a lot of assumptions here. So if you think you have any better insights on the numbers we have used, or like can help us maybe limit some of the rather wide assumptions we have made to try to be as inclusive as we can, then certainly would like to hear back from you.
Yeah, absolutely. Agree.
Amazing. Great. Well, we will wrap up there then. Thank you so much, Mirjam and Georgios, for your time and valuable insights. And yeah, it's great to see this future and horizon based scenarios, because I think it certainly gets people thinking. So thanks so much for that. And yeah, don't hesitate to be in touch with us or Mirjam and Georgios directly if you have any more questions or any insights to share.